Alright, it's time for another math. Easy solution. I'm going to discuss further into limit laws, part 2 of that limit laws series, which I had, and I'll do examples on the part 2. Basically, I have the earlier video I did. You can see the video link below, and also go over what the direct substitution property is and do an example on that quickly. Basically, the limit laws here are supposed to see as a constant and limits below exist of x to a of fx and g of x. You can see these. I have 11 laws I've written down in my earlier video. I'm not going to go over them, but there's the sum, difference, constant, multiple law, product, quotient laws, and then we get to the power and root ones here. But you can see a video linked below for more in-depth discussion on these laws and also a brief history of limits in Newton. And basically, let's look at the example here. Basically, evaluate the limits and justify each step. So let's write down right now. Okay, so we'll just look at this example here, example A first. Basically, it says evaluate the limit and justify each steps. So what I mean by this, just apply the laws stated above on this example here. Because well, this one here, you know, that's a rational function here. You could just probably just plug in. You could just plug in the number 5 and get the answer. But if we want to use the above laws to be strict here, what we could do is apply the laws 1 and 2. Yeah, so apply these laws first. And if I scroll up here, basically laws 1 and 2, it just states if you have a sum or a difference limit inside. So if the limit outside of these, then you could just put the limit inside of these each one. So from here we could get limit as x approaches 5. Now this becomes, then we just do it of each single inside this bracket here, or the sum and differences here. Alright, so we get, now we get this one here by applying the laws 1 and 2. Now we can apply laws 3, and we apply this law 3 here, basically the constant multiple law, to get these constants out. And that's just from here, the constant multiple. So if you have a constant in front of the function here, then you can just take the limit of the function and the constant goes out of there. Yeah, thus we get limit x approaches 5 of, then we put the 2 out here actually, and this is x squared. Similarly here, 3, yeah, limit x, so that 3's out there, and we also do the same in here. I'm going slow here just so we could show every step here using the limit laws. So now we could apply laws 9, 8, and 7, basically just to solve these ones out. And laws 9, 8, 7, just to recap here. So if you have the power one here, as x goes to a, you just plug the a inside. And then if it's just a constant, like, I mean, if it's just limit of x, you just put the a inside. And also, if it's a constant, it just equals to the constant. So if we apply those, we're going to get now, this is going to be 2 times using that power one, or law 9 power rule. Just put that in here. We're going to get 5 to the squared. And then minus 3 times, put this 5 inside the x. So this is 5. And then plus, this is a constant, it just becomes constant by law 7. So 4. So then we multiply these out here. This is 2 times 25 minus 15 plus 4. This equals to now 50 minus 19. Oh yeah, minus, let's see, what is this going to be? These add up to be negative 11. So minus 11 is equals to 39. So our limit is 39 here. So now, yeah, this was pretty straightforward in 39. Now, let's go to the second example here. Basically, limit as x approaches negative 2 of this quotient here. x3 plus 2x squared minus 1 divided by 5 minus 3x. First thing we could do is apply the quotient law, or law 5 here. And the reason we're doing that is just because if you look at this one here, so we could just separate these two different kind of functions by putting the limit on top and bottom here. This is only if the bottom is not equal to 0. So yeah, so first thing you have to do is check the bottom. The denominator, if you just plug the negative 2 inside here, you're going to get, let's say, 5 minus 3 times negative 2, this is going to be plus 6, so it's going to be 11, and it's not equal to 0, so we're good. So we could apply the quotient rule here, and this is going to equal to now limit, well actually, yeah, limit of the top, then divided by limit of the bottom here. Now we could just do similar to what we did in part A, and basically just use the laws 1 and 2, yeah, and actually laws 3, and the top and bottom separately, so we could get these separated as difference and sums, and also this constant multiple, just 2 and 3 out of there. So we could apply that. We're gonna get, so yeah, we're gonna get this one right here. So we separated every single sum and difference and took the constant multiple out. Now we just apply laws, basically 9, 8, 7 to basically just solve for these power and this x function, this linear function, also this constant one here, and we're gonna get now, it's gonna equal to, we just put this negative 2 inside, we're gonna get negative 2 to the 3 plus, we'll just put this bracket here, plus 2 times, this is going to be negative 2 squared, minus is constant, just put the 1 in, doesn't matter what the limit is approaching, then divided by right here, put this here, we're going to get a 5 minus 3 times negative 2 right here. So we're going to get, in this case here, is going to be negative 8 on the top, is it's negative 2 times negative 2 times negative 2, and plus 2 times, it's going to be 4 minus 1 divided by 5 minus, or 5 plus 6. So we're going to get now in this one here, this is an 8. So it's 8, negative 8 plus 8 to cancel. So we're going to be left with negative 1 divided by 11 here. This is our answer. So now I want to make a note on these two examples. Basically, if we directly substituted the x value into equations A and B, we will get the right answer. So what I mean by this, is if you look at part A, we basically had limit this limit here. So if we let this limit equal to f of x right here, so we'll go f of x is equal to that function here, this limit here. And now if we just plug in f of 5, we're going to get now 2 times, well, this is going to be 5 squared minus 3 times 5 plus 4, and you solve this, we're going to get 39, which is the correct answer. Yeah, and similarly for part B, we're going to, if you let g of x equal to that limit, we're going to just plug in negative 2, we're going to get negative 1 over 11 here. And these are correct answers here. And the reason we could do this is actually, it's because this was just a rational, and it's just a polynomial, so it's a continuous function. Yeah, this is true, yeah, because this property that we just showed here, just directly substituting them, is always true for polynomials, which was the equation in part A, and rational functions, which is equation in part B here. And I will prove this later, but you can see, just applying the limit laws, we're going to get just a direct substitution property here. And also, basically, in general, I'll just write down this property. So basically, in general, the direct substitution property states if f is a polynomial or a rational function, which like the above two equations, and a is in the domain of f. So basically, this is so f is defined at a or whatnot. Then basically limit as x approaches a of f of x equals f of a. So what I mean by this, a is in the domain, meaning it's continuous, and also, and that's what was stated here, functions with this direct substitution property are called continuous at a, or at value exists. Not just the limit to actual value, it exists, and not all but the thing is, not all limits can be evaluated by direct substitution, such as limit as x approaches 1 of x squared minus 1 divided by x minus 1 here, because with this one you can't plug in a 1 here. You're going to get a basically 1 minus 1 divided by 0 here, or 0 over 0. This is not defined here, so you can't just do this right here. Yeah, it's not defined, and I will solve this next time here, and also I'll prove this direct substitution property in general for polynomials and irrational functions here. Well, that's all for today. Hopefully you learned from these examples, and also, yeah, just a bit on direct substitution property. Hopefully you learn about that. I'll do examples on that in later videos, and that's all for today. Remember, you can download these notes in the Dropbox link below, and stay tuned for another Math Easy Solution.